Welcome everyone to another video. Today I want to talk to you about the Es'Hail-2 satellite. Now this is something that many of you probably already know about, but I imagine there are some of you that do not. So a short introduction, even though I have mentioned it in previous videos as well. Es'Hail-2 is a satellite, it's a TV satellite in geostationary orbit. It is by all means not particularly interesting when it comes to broadcasting and telecommunications satellites. I believe it has Ku band and Ka band payload. It provides services for Qatar, of course, the Middle East and North Africa. The thing that makes this satellite stand out, and that makes it arguably one of the most interesting geostationary satellites currently in orbit, is the fact that it is the very first satellite in geostationary orbit to carry an amateur radio payload. And the only satellite currently still. This satellite, sitting roughly at 38,000 kilometers above the Earth's equator, carries a repeater for amateur radio that anyone with a license can freely use. And the goal of this video, and hopefully upcoming videos about this satellite, is to actually show you what you can receive from it, and eventually also how you can transmit through it, how you can make contact with other people through the satellite. So just to get two things out of the way right away. For now, I'm only going to be focusing on receive-only applications. I believe it is still quite interesting trying to receive it and seeing all kinds of traffic on this satellite. There's SSTV, right, short scan television pictures, of course SSB voice. It's kind of like an amateur radio HF band that has been lifted all the way to 10 gigahertz. The other big thing that I kind of wanted to not really mention in the beginning of the video because it's going to kill the retention, but this satellite, because of its position to serve the Middle East and North Africa, it's sitting, I actually forgot, I don't know, like 30 degrees east, which in practice means that you cannot receive it from North America. If you are outside of its footprint, which I will be putting on screen right now, you cannot receive this satellite, unfortunately. There are some plans for an American satellite built by Americans for Americans, but I'm not entirely sure how that's going. Maybe we're gonna have a video on exploring that as well. But yeah, for today, for Es'Hail-2, unfortunately, it has a fixed footprint. Es'Hail-2 in the amateur radio circles is more known as QO-100, which is its amateur radio designation, or its AMSAT designation, of course Qatar Oscar 100, and that's generally how I'm going to be referring to it. Receiving this satellite is incredibly easy. I would even go as far as to say that it is the easiest amateur radio satellite. I don't want to say ever, that's a bold statement, but I think it is currently the easiest amateur radio satellite that you can set up a receiver for, even a transmitter for. That is because, well, together with the fact that it's in geostationary orbit, which means you just set up an antenna like this. This antenna actually has been aligned with Es'Hail-2, with QO-100, and it's aiming permanently at it. I don't have to touch anything. It's always going to be getting perfect signal as long as it has clear line of sight. Together with that, there's also the fact that it uses the 3 centimeter amateur radio band for its downing, which, if you don't know, is around 10.5 gigahertz, which, if you still don't know, is right at the lower edge of the range of frequencies that commercial off-the-shelf Ku band TV LNBs actually work at. Both of these cost, I don't know, like $5, and they are working perfectly fine for the reception. Combined with the fact that a small aperture dish antenna works, something like this, or even this dish antenna works perfectly fine and has enough gain for it. So what all of that compounded means is that you can take whatever setup you have, or you can buy, or you can find for free. Usually you can just take the entire thing and reuse it for QO-100, although I would recommend buying a new PLL LNB, making sure it's at least somewhat stable. We are going to be taking a look at that in this video in more detail. I recorded a section with a practical demonstration of how you can receive this satellite. Unfortunately, the audio was horrible. I didn't actually have a cool setup like this, so I was just talking into the microphone of the iPhone, and it's not great. So I am going to put some clips from that in this video so you can actually see a practical demonstration. So to receive this satellite, the very first thing you have to ensure you have is clear line of sight. Again, I have shown it before. I'm gonna put it on screen now. This is the footprint of the satellite, where you can expect to be able to receive it with somewhat small antennas. You can probably go a bit further than that if you have a bigger antenna, and you can put it higher so we can see basically effectively under the horizon, right? The other thing, the second most important thing after having line of sight with a satellite, is having an antenna. Now, this satellite, the downing, at least on the narrowband transponder, is so stupidly strong that you can just take the LNB from the dish antenna, aim it directly at the satellite, and I believe I have actually done that in the clips that I'm going to be showing, and that is enough. I think at one point I just dropped the LNB on the ground, and it just happened to land in an orientation that was enough to see the beacons coming through the transponder. You will want to have a higher gain antenna. I would say an 80 centimeter dish like this, like one of those, would be ideal because it's not too big. Something like this works as well. This is also enough to peak the strength of the transponder. You want to make sure that the LNB you are getting can receive 10.5 gigahertz. Usually these LNBs are going to be marketed to only work from up to, I don't know, do they have it? 10.7 gigahertz up to 12.7. That's actually the TV range, right? The Ku band TV range that was written on the LNB, but realistically they can go down to 10.5. I'm just mentioning this specifically so you don't get some special kind of LNB that only goes down to 11 gigahertz or 12 gigahertz, because those also do exist if you just browse AliExpress for it or something. You have to make sure that the LNB you are getting is a PLL LNB. PLL refers to the type of technology used to actually generate its local oscillator frequency. Again, as usual, 75 ohm coaxial cable using with 50 ohm SDR doesn't matter. You don't have to worry about that, especially not in this case where the conversion gain of the LNB is absolutely insane. And that actually is a good thing I'm mentioning that. If you want to stay on the safer side, you may want to consider buying an attenuator to put between your SDR and the cable that's going to be feeding it from the LNB, because the conversion gain of the LNB is usually very high. It's meant to push all of that signal through a lot of very lossy cable. I personally don't use it. I don't want to give an example that it's okay to do that. It's probably safer to use one, I don't know, put like a 5 or it's probably not enough, 10 to 20 dB attenuator. I do think I have a 16 dB attenuator and I use it sometimes. You can generally get all of these things that I'm going to be listing off in just normal satellite TV stores or buy them online. Yeah, right, that's the big thing about QO-100. You can work it with hardware that's not meant for amateur radio at all. You can just get it anywhere. So yeah, the attenuator may be worth considering. Before we get to the SDR, we also need a way to power the LNB. Now some SDRs, again I have mentioned that in the Ku band video, some SDRs do actually have bias Ts, aka a way to inject 5 volts of direct current into the coaxial cable and power whatever active antenna you have connected on the far end. LNBs, they are going to need 12 volts to 18 volts. Aim for 12 volts. When you supply an LNB like this, 12 volts is going to be working in vertical polarization. Not only can you not do that with an SDR bias T, I also don't think it's safe to supply an LNB from a USB port. I mean, I have done it in the past using a DC to DC step-up converter from 5 volts from a dedicated USB port. Depending on the LNB, they may draw more current than your USB thing can supply. Maybe USB 3 maybe would be fine, I don't know. And then of course you need a way to actually inject those 12 volts DC into the coaxial cable so it can get to the LNB. I am again using off-the-shelf bias T power injector. Again, intended to be used with LNBs like that. It's very convenient because it just has a female barrel jack connector, and I'm using a wall power adapter that in the video example is actually connected into the fridge over here. Don't think about that too much. We just have wall power to 30 volts converted into 12 volts being injected into the coax, sent to the LNB. That's how we are powering it. A couple things about using a power injector like that are sort of important to keep in mind. Do not power an LNB or any active antenna for that matter without a proper RF load connected to its output. The bias T itself does not count because the bias T only lets the RF pass through. You do want either a 50 ohm dummy load or at least have the SDR connected, even though it's not connected to a computer. Another thing is the, I guess, direction or polarity of the power injector, where you have 3 connection ports. You have your DC connector, right? That's where the DC input comes from. You have an RF connector, which doesn't let any DC through, and then you have an RF plus DC connector, which actually that's where the DC current gets injected. Obviously, the RF DC side has to be facing the LNB. You do not want to send 12 volts DC into the RF input connector of your SDR. That's a quick way to damage it, so it's always worth making sure you have everything connected properly before powering it up. After the bias T is where you would put your attenuator. You do not want to put the attenuator between the bias T and the LNB. After that we have the SDR itself, and between that you would need like an F connector to SMA adapter, again relatively cheap to get. And finally we get to the SDR itself. Again, as I said, even though the frequency is 10.5 gigahertz, the LNB is actually converting it down to like 700 something megahertz. I don't know, I can do math. So any SDR, any general SDR is going to work. There is no special consideration, I don't think, for the SDR, especially because of the massive conversion gain of the LNB. So when all of this is connected up, you are ready to power up your setup and find the satellite. You can use like satellite finder apps to give you a rough idea of where Es'Hail-2 is, because that's how it's probably going to be named in those, because those are meant for TV reception. Actually, this is one thing that I forgot to talk about that I actually show in the clips that I recorded. If you have a satellite TV antenna like this already on your house, there's two scenarios, right? You have it and it's unused, you have stopped using it, you have switched to online streaming or terrestrial TV. In that case, you can just re-aim it at QO-100, maybe replace the LNB if it's old, maybe replace the coax if it's old. If you have an antenna like this and it's still actively used for TV reception, you may still actually be able to use it for QO-100 as well. This is something that I have showed in the clips that I recorded, where you can just buy a second LNB and put it offset next to the actual actively used LNB. Right? This is a multi-focus configuration. It is commonly done to receive multiple TV satellites at once using a single parabolic antenna. It does slightly lower the overall gain and efficiency of the antenna the further the LNB is offset from the original focal point. But again, with QO-100 it doesn't matter, and because you have an antenna like this, you have enough margins to not care at all. You can get a bit creative with how you mount the LNB. In my case, I wanted to demonstrate just how super easy it can be, so I just ran like a solid core copper wire and the LNB was sort of hanging there, and it was enough to receive a satellite at full strength. Of course, you would want to do something more permanent, something more durable than that. Yeah, aligning the antenna, that's what I was talking about. It can be a bit difficult to first find the satellite, but once you do, it sort of sticks in your memory. And I'm going to be going over the software. I have an entire section on that, but I actually forgot to talk about that even in the original recording. The frequency that you want to be monitoring. So when you first power everything up and look at your SDR in the software, what you want to see when you power up the LNB, right? So you can set up everything, connect everything except the power input of the LNB. You're going to see noise floor of the SDR, and then you power up the LNB, and what you should see is the noise floor jumping up as the LNB starts up and starts amplifying random noise coming into the dish antenna. If you don't see that, maybe you can try raising the gain of your SDR, or maybe you have a loose connection somewhere, but that's generally the indication of the LNB is working. Once you have the LNB powered up, you have to calculate the frequency where QO-100, the narrowband transponder, is being down converted to. The center frequency of the QO-100 narrowband transponder is this. Then you have to subtract the local oscillator frequency of your LNB. In my case, it's 9.75 gigahertz, and you get the resulting IF, or intermediary frequency, which is where your SDR wants to be listening at. There is usually an option in the SDR software, like SDR++, SDR Sharp, SDR Console, where you can actually input the local oscillator value of your LNB, and it does that subtraction, that calculation for you. So in the software, you would be typing in 10.5 whatever gigahertz, 10.49 whatever gigahertz. I don't remember it off the top of my head. I'm sorry, I have the band plan saved because of this. And the software would automatically be tuning the SDR in the intermediary frequency while displaying the real RF or radio frequency, right? Oh my god, I'm starting to lose my voice already. The LNB without any frequency compensation can be quite a bit off, which means the local oscillator is not going to be exactly as advertised, and that's normal. That usually doesn't matter at all with TV, with satellite TV signals that are multiple megahertz wide, but with this, it actually does matter. So what I suggest you do is, when you are first looking for a satellite, set your SDR to at least 2 million samples per second, just in case the LNB's local oscillator value has drifted that far from its intended frequency. It's better to look with a wider bandwidth. After that, it's simple. Once you find the signal, you want to roughly aim your antenna and then just tighten the bolts or whatever, make sure the antenna is fixed at its position. The satellite is not going to move, so you can just fix your antenna aimed always there, and you are set up technically. Okay, yeah, actually, one important point. Depending on where you are in the world, you may have to adjust your LNB skew, which is the rotation of the LNB in a holder like this. This also applies to TV satellite reception, so I may probably be better for you to just look it up online. All that means is, all you are doing by this, and usually LNBs have a little angle scale printed on the top for the skew adjustment, you are aligning the little vertical probe inside the waveguide of the LNB to be at the same angle as the polarization from the satellite observed from your point of view. When you do find a signal and you maximize its strength by aligning the dish antenna, the last thing you can try doing is slowly rotating the LNB and seeing at what orientation is going to give you the strongest signal. And I think I have sort of talked about everything there is to the actual reception of the satellite, right? So I'm now going to hand it off over to me like 2 days ago, and we're going to go over the software setup to actually show you how you can compensate for the frequency drift of your LNB in software, which is actually really important. It's actually a requirement if you want to receive anything interesting from the satellite. And in future videos, I'm not sure if it's going to be the exact video after this, but in future videos about the satellite, we are going to be taking a look at the actual traffic that you can encounter, the actual radio traffic that you can encounter on the transponder. Most prominently for our receive-only applications without a license when you are not transmitting would probably be image modes like SSTV or digital image transmission modes. There's of course, as I said, SSB voice, there's plenty of Morse code, there's FT8, there's all kinds of stuff. And then of course, as I said, eventually we will be taking a look at transmitting through that satellite and contacting other people across the 30% of the planet that the footprint of the satellite actually covers. So that's it for me for now. Outside here, there's another plane here. So that's gonna be it for me here, and now we are transitioning to the low resolution laptop screen recording. So enjoy that part of the video, because I sure did not. Okay, well, here we are. I have actually installed OBS. I did the thing I said I should do. And well, let me welcome you back to the 768p laptop. I don't know what resolution this is. It's what we're gonna have to deal with. We got SDR++ open. I am hooked into the dish antenna, which is currently aimed at QO-100, just as you have seen before, except this time you're actually seeing the screen without looking at my dumb reflection in it. Zoom in a little bit, and you can see the blue sections. Those are sort of the reserved guard bands for the beacon. We can actually pull up the band plan online, and this is sort of the same structure we see in the SDR. We have the 3 guard bands, or the 3 reserved bands for the beacons. Over here is the CW beacon, or constant wave, or Morse code, you could say. It's using 2 alternating frequencies. So I'm gonna turn on the audio. It's gonna be kind of garbage, but now we can go to the central beacon, which I think is this. Wonderful sound, really. What a great day to have ears. And here we have the upper beacons. But again, the big thing, right? It doesn't align with the band plan. And not only that, when I actually let you listen to the beacons, and I'm gonna do it again with low bandwidth, so it's not like horrible. Okay, well, this is this is not going my way. Basically, you can hear that the frequency is slowly drifting, right? The tone, the pitch of the beacon is shifting a little bit. And this is actually caused by our LNB. The actual local oscillator frequency of this LNB is 20 kilohertz. Am I saying it correctly? Yeah, 20 kilohertz higher than what it's supposed to be, right? LO is higher, that means the perceived frequency is lower. This is actually a horrible example for what I wanted to show you, because this is actually not bad at all. The one I'm using here is literally the cheapest LNB I could have found brand new for sale, and look at that. We are just 20 kilohertz off. That's great. But you're gonna have to kind of take my word for it, and I bet any kind of longer term usage, you're gonna notice this as well. Currently, the conditions are pretty much perfect for this LNB to do its best it possibly can, because the sun just now set, which means there's no direct heating on the LNB. There's absolutely no wind whatsoever, so there are no rapid temperature changes on the LNB. Anyway, my point is that the frequency does drift, and currently it is drifted like 20 kilohertz down. It's possible that as the LNB heats up throughout the day, the frequency is going to go another 40 kilohertz up, and it's kind of going to oscillate around 9.75 gigahertz, right? It's not going to be perfectly stable. And this may not be an issue for things like voice, where you are only like short-term listening and you can nudge the frequency manually. But for modes like SSTV or other digital modes that use frequency shift keying, this is actually quite bad. And well, for something like KGS-TV, which you may not know what it is, it's basically a digital mode for transmitting images. We will be taking a look at that. Even this slightest sort of drift that that's almost imperceptible in the short term, it's enough to completely ruin your reception. You could manually change the offset or something, but we do have the technology to fix this. This is where SDR console comes in. Okay, SDR console, there it is. It's so cool that it doesn't even have, it's just called console. Okay, I'm gonna close SDR++, you're gonna stare at the OBS screen. Look at that, look at the cool splash screen. There we go. Now I already do have it configured. Okay, it's a little sluggish, but that's okay. I already have it configured for QO-100 reception, but probably should reset this, right? Okay, so I need to open it again. I already had it configured for QO-100, and I want to actually show you how it's done. So I have undid all those changes. So there it is. There's SDR console. When you turn it on for the very first time, it's gonna tell you this: radio definitions. You have not added SDR definition to the program, at least one radio must be. So you go to definitions. Oh, search. Okay, I'm an idiot. You have to go to search, not add. You have to search for the SDR because the SDR is connected via USB. So we go to RTL dongle and USB. Of course, this is the new like any SDR, but as I've said in all of my previous videos, by software and by hardware, it's considered an RTL SDR because it's the Realtek integrated circuit. So it found it, and we add it. Make sure all your other programs are turned off. That's why I closed SDR++ to make sure nothing is claiming the dongle. And there it is. That's our little SDR. And now we can save this. Now we select it. Select our bandwidth, and for QO-100 750 kHz is fine, and it should start. But of course, turn off the audio for now. It's not going to be at this frequency first. I'm gonna be completely real with you. I have not really figured out SDR console because the UI is very, very different from things like SDR sharp and SDR++. So this is something you're gonna be seeing right when you first open this thing. I don't know what this is. I don't know what any of this is. We are here for QO-100. Okay, let's just take that and leave. Let's tune to the QO-100 frequency. Well, how do we do that? We don't have the converter defined here like we had in SDR++, which was recalculating the frequency, but that's okay. We can do it manually, right? Which is around 790. There it is. Look at that. Okay, there we go. This is what I wanted to see. We are receiving QO-100 in SDR console. Now, right now, we have the same issues that we had in SDR++. Well, first of all, the frequency is completely wrong, right? This is the intermediary frequency. For convenience, we would like to see the actual radio frequency of the satellite. So we're gonna stop again. This takes a while, I don't know why. Go to select radio and converter. There's nothing. So we have to go to the definitions, converter selection, make sure this is enabled, go to edit, and we add our converter. It's a down converter for RX only. Call it an LNB, call it whatever you want, I don't really care. And this is the frequency in hertz. So, okay, hold on. I don't know why it's made like this, but it's megahertz, right? So now 9750 megahertz. Okay, even though we have learned that the actual local oscillator of the LNB is not exactly this, it's never going to be any exact value. It's just going to sort of drift around this frequency. So that's what we are putting in. Let's apply. That creates our converter and save that. And now save again. Before clicking start, we select our SDR that we have defined, and we can select our converter that we have defined. Now click start. And what's going to happen is absolutely nothing because we are still tuned to the IF frequency. It's just using the IF frequency. So now we can go to 10.5 gigahertz, right? Well, look at that. We can't, because this thing maxes out at 9,999 and so on megahertz. This is something that took me a while to figure out. I don't know why. I don't know why it's even done this way, but whatever. You have to go to the View tab, go to Options, and here change the frequency range to 99.9. Okay, and nothing happens because we have to restart the program. But if we are already restarting it, we are gonna do one more thing. Go to this button, More Options, select, and here we have the geostationary beacon thing, plugin. I don't know if it's a plugin, maybe, let's call it a plugin. Press OK, now it says restart now, so we restart SDR console. And there we go, look at that, we have just gained a digit here. Okay, now we can actually go, not 19 gigahertz, but 10. By the way, right-clicking it changes it to 0, right? 10490, and there we go, look at that, that's our thing. Let's tune to the beacon, because that's the center frequency, and center it on there like this. So now we have basically gotten to the exact same situation as we had in SDR++. We are receiving the signal, we are displaying the down converted frequency. Let's see, did the LNB drift? Not really, it's actually being really stable, but okay, we're gonna make it even more stable, okay? That's what we're doing here. Now go to tools, okay, go to view, not tools, and here the geostationary beacon option appeared. We're gonna open that. This window opens. Again, this is kind of confusing to me, but I know how to make it work. That's all we need to know. Let's zoom out the window, right, until we can see the central beacon that's over here. What we have to do in this window, and you are probably already figuring out what this does, in this geostationary satellite beacon window, we actually have to find the central beacon of QO-100, center on there, and now press enable. And watch this IF display. Actually, I'm gonna put it over here. And here we can see the band plan is misaligned with the beacons. Here's the lower beacon, it should be here. The central beacon is here, it should be here, and so on. So now when we press enable, watch what happens. Boom. And we are locked. We are currently locked. We are synchronized with the satellite, and our frequency is now being basically recalculated and readjusted to make sure everything is correct. So now we can just double check. The central beacon should be 10.489.75, right? That's in the center. So let's go to 10.489.75. And look at that. It is correct. I was wondering why it's offset. It's of course because we are using single sideband demodulation, so the actual center frequency is here and we are only listening to the upper portion of it. If we go to, let's say, narrow FM, look at that, now we are centered. So this was just a visual thing, but the beacon is now perfectly stable. I still haven't figured out the GUI. You're gonna have to do that better than me. Oh, look at that, someone is spectrum painting. What a nice thing we have just seen. Anyway, so this is how you set up SDR console with QO-100, and now it is actively compensating for the frequency drift of the LNB. Be careful when you are tuning around, zooming in and out. Make sure your thing is always centered at the beacon. We could probably like hide this somewhere, right? We don't really need it. Right, now we are set up. Let's say you see a signal. Look at that, there's a signal here. We can click it. What a wonderful sound. This is actually FT8 traffic. The frequency wobble there is intentional. That's how it encodes the data. In the next video about this satellite, which is probably also the next video in general is going to be on my channel, we are going to be looking more in depth at this band plan and the actual types of transmissions that you can receive, and maybe we're gonna take a look at decoding some of them, but I would like to cover those in like their own separate videos. I've promised to myself that I would make a shorter video this time, but well, there we go. So let's not drag it on. Thank you for watching and stay tuned if you are interested in this, and I will see you in the next video.